kind of seen a whole bunch of different molecules with molecular orbital theory, mostly linear molecules, but one example already of a molecule with 2 dimensions in a plane. We're ready to move on to an even more complicated molecule, ethene, or ethylene, C2H4. The IUPAC name is ethene, the common name is ethylene, from which the polymer polyethylene is made. And it's an unsaturated hydrocarbon with 2 fewer hydrogens than the saturated system would have. We know that there are 12 atomic orbitals. In the valence shell. 4 each have 2 carbons, and 1 each times 4 hydrogens. And we know that the molecule is planar, and that the carbon is sp2 hybridized. Having 3 electron groups around each carbon, and having bond angles that would therefore be pretty close to 120. A little bit different because this carbon is not identical to the 2 hydrogens, so it's going to be a slight modification of that 120 degree bond angle. But basically trigonal planar geometry around carbon and sp2 hybrid. We have a single pi bond here, and that pi bond is out of plane. So we know that the pi bond is formed by overlap of the 2pz orbitals on each carbon. So we'll form pi z. With a lobe out in front of the board and a lobe back behind the board, and the anti-bonding combination pi star z with a node between the nuclei as well as the node in the plane of the board, 2 lobes out of phase in front of the board, 2 lobes out of phase behind the board. And these orbitals are common to both the valence bond picture and molecular orbital picture. Where the 2 approaches differ will be in the formation of the bonds in the plane of the molecule. So if we look at a valence bond picture and use valence bond theory to look at the bonding in ethene, we would say that there's a carbon-carbon bond being formed by overlap of an sp2 hybrid orbital on each carbon to form a sigma bond between the 2. And then we would say that there's another sp2 hybrid orbital on the carbon overlapping with a hydrogen 1s orbital, again to form another sigma bond. And that's going to be repeated for each of the other hydrogens. So we form a total of 5 sigma bonds. And 1 pi bond, representing the 6 bonds in the molecule, 4 identical carbon-hydrogen sigma bonds, and then a carbon-carbon sigma bond, and a carbon-carbon pi bond. And usually when we talk about valence bond theory, we ignore the anti-bonding combinations. So in each of these cases, this sp2 to 1s interaction would be constructive, forming the sigma bond, but there'd also be the corresponding out-of-phase destructive interference, which would create an anti-bonding bond orbital caused by the 2 sp2 generally, that's not what we think of when we draw a valence bond here. We would draw this picture, and then we would layer on top of that the pi bond. It's nice that the frontier orbitals are always in the pi system. So these will in fact be the frontier orbitals. The pi orbital will be the HOMO, and the pi star orbital will be the LUMO, and together those will be the frontier. And that'll actually stay true in the orbital picture, just as it is in the valence bond picture. So if you want to understand how the alkene, or the carbon-carbon double bond, interacts, you can understand that by knowing that a Lewis acid would be attacked by the electrons in this pi orbital, and if a Lewis base attacked, if the Lewis base is attacked, one of the lobes of the empty pi star orbital. So we don't really need to even know what the in-plane framework of the molecule looks like to talk about reactivity. But it's an interesting application of electroorbital theory to think about what the in-plane framework would look like, and we can certainly do it using the same approach we did for acetylene by treating the C2 unit as the central atom. And creating ligand group orbitals for the 4 hydrogens. So it'll be very similar to what we did with acetylene, except that now instead of having just 2 ligand group orbitals for 2 hydrogens, we'll have 4 ligand group orbitals for the 4 hydrogens, and then we'll drop the same C2 dimer, and we know what the orbitals look like for the dicarbon molecule. And so we should be able to do that. So the first challenge is to actually create the ligand group orbitals. And it's actually easier to create the ligand group orbitals for ethylene than it is for boron, because since those hydrogens lie on a rectangle rather than on a triangle, we won't have any ligand groups orbitals where the nodes have to go through nuclei. So we will have no orbitals that have 0 coefficients. So we want to think about the relative position of the 4 hydrogens on a rectangle like this, and we know that the lowest energy orbital will be created with all of those 4 hydrogen 1s orbitals in phase with one another. So the hydrogens are in the center of those, the 2 carbons are kind of lying here in the middle, and again, there's no actual overlap because those 1s orbitals are far enough apart that within the 90% or 95% confidence interval, we're not seeing any actual overlap of the wavelength. And that's true whenever you do the ligand group orbital. So this will be the only way to have no nodes. And then we can have an orbital that has a single node on the vertical plane, which would have the 2 hydrogens on the left out of phase with the 2 hydrogens on the right, but in phase with each other. But we could also have a single node on the horizontal plane, which would have the 2 hydrogens on the top, 2 hydrogens on the bottom, and those should be expected to be degenerate. Lambda 2, lambda 3, because they each have 1 node, should be at the same energy. The other possibility, right, there's only 2 ways to cut a piece of paper in half. So once you've done that with the vertical node and the horizontal node, you can't have another single node orbital. You'd have to have a 3-dimensional molecule to have another orbital at a single node, and in that case, the node would be the plane of the page, or the board. So the only other way to do it is to have 2 nodes on the vertical and horizontal plane, and have all of the orbitals out of phase with the orbitals adjacent to them. And that would be higher in energy. So if we wanted to put these 4 ligand group orbitals on an energy diagram relative to the 1s orbitals that we start with, lambda 2 and lambda 3 would in fact be non-bonding orbitals. Lambda 1 would be down here, lambda 4 would be up there, and they would be filled like so. Of course, ligand group orbitals don't actually exist, right? They're just a construct that we're using to help us get from the atomic orbitals to the molecular orbital picture. So we can think about how many possible molecular orbitals there can be, and they have to be 12. Because there are 12 atomic orbitals, we have to make 12 molecular orbitals. 10 of those are in plane, and 2 have pi symmetry. And as we said, the pi symmetry orbitals, pi z and pi star z, come from the 2pz orbital on each carbon. So we have these 4 ligand groups, and we have to combine those with the C2 dimer orbitals, right? 6 of the C2 dimer orbitals. And remember that the C2 dimer looks like this: sigma 1g, sigma 2u star, pi y and pi z, sigma 3g, pi star y, pi star z, and then sigma 4u star. Pi z and pi star z remain unchanged. In C2H4, because those are the 2 that are out of plane. But the others, sigma 1g, 2u, 3g, and 4u star, and then the pi y and the pi star y, those lie in the plane. So we'll be combining those with these ligand group orbitals to create a new set of molecular orbitals. And C2 dimer again has 8 electrons, so sigma 1g, 2u star, and 2 pi bonding orbitals will be filled. And we know that sigma 1g is one big orbital, mostly between the nuclei. Sigma 2u has a single node and very little electron density between the nuclei. Pi y has that load above and load below. Sigma 3g has large loads outside and only a small load between the nuclei. Pi star y is that stretched cloverleaf, a node between the nuclei as well as a node in the XZ plane. And then sigma 4u has large amounts of electron density between the nuclei and not much electron density outside the nuclei. So the ends, sigma 1 and sigma 4, have large electron density between the nuclei, and the middle sigma orbitals, sigma 2u star and sigma 3, have relatively low electron density between the nuclei. So now what we have to do is we have to identify the symmetry properties of these orbitals and match them up with the symmetry properties of the ligand group orbitals so we can see which ones are capable of interacting with each other. So you can see that lambda 1 is errata with respect to reflection through the XZ plane, but it's also symmetrical with respect to the reflection through the YZ plane. So regardless of whether I cut it in the horizontal or the vertical plane, it's errata. Which orbitals in the C2 dimer have that same property? The subscript on sigma 1g and sigma 3g tells you that they're errata with respect to reflection through the vertical plane, and all of the sigma orbitals, all 4, are errata with respect to reflection through the horizontal plane. But only sigma 1 and sigma 3 are errata with respect to reflection through both those planes. So lambda 1 is going to be able to interact with both sigma 1 and sigma 3g. Lambda 2 is errata with respect to reflection through the xz plane, but ungerade with respect to reflection through the yz plane. That symmetry matches the other two sigma orbitals on the C2 diamond. So lambda 2 is going to interact with sigma 2 u star and sigma 4 u star. Those combinations are directly analogous to what we saw for acetylene. Right? The only difference being now we have 4 hydrogen 1s orbitals instead of just 2. Acetylene would put these 2 carbons right between there instead of down below. So we're going to have a very similar arrangement. We have 3 orbitals and thus 4 possible combinations, but 2 of those solutions will be degenerate because we're only allowed to form 6 orbitals from 6 leading group and bonding orbitals from the C2 dimer, not 8, and there are 8 possible combinations. Lambda 3 has the same symmetry as pi y. It's gerade with respect to reflection through the vertical plane, but ungerade with respect to reflection through the horizontal, the xz plane. Gerade for yz, ungerade for xz. Pi y satisfies that. So we will create an orbital that's lambda 3 plus pi y, and we will create an orbital that's lambda 3 minus pi y, and there are only 2 orbitals with that symmetry, which will make it easier to do. Lambda 4 has the same symmetry as pi star y. It's ungerade with respect to both reflection through the vertical yz plane and reflection through the horizontal xz plane. It's the only orbital that has that symmetry. So lambda 4 will interact constructively with pi star y, and lambda 4 will interact destructively with pi star y. And since there are only 2 possible combinations, that won't be particularly difficult to create either. These are the more complicated ones because in these cases we have 3 orbitals that have the same symmetry properties. So let's start here with the combination of lambda 4 and the pi star, the anti-bonding pi y orbital. The constructive overlap would have the pi star orbital interacting with the ligand group so that we get constructive interference in all locations, and we get a bulge and basically what we're going to get is the same cloverleaf shape that we had from the pi star orbital, but now extending out and including the hydrogen nuclei. And you'll notice that I changed the sign here, but it was arbitrary whether I started with plus or minus, so I can put that into the same plus and minus orientation as my lambda 4. So this will be one of the molecular orbitals that's created from this combination of lambda 4 with the pi star orbital. It has no new nodes, but still has the same 2 nodes that it started with. The anti-bonding version of that, if we flip the sign on the pi y orbital, but leave the sign the same on lambda, the ligand group, we now have destructive interference, and we're creating new nodes between each carbon and its hydrogens that are attached. We still have the two nodes that came with the pi y orbital. So what that would look like is going to have a lot of nodes, a lot of different loads. So we have new nodes, new nodes, in addition to the existing nodes that were there to begin with on the horizontal and vertical. So that's anti-bonding with respect to everything, right? It's anti-bonding with respect to the carbon-carbon bond, and it's anti-bonding with respect to all the carbon-hydrogen bonds. This flow orbital is bonding with respect to all of the carbon-hydrogen bonds, but still anti-bonding with respect to the two carbons. Well, what about the combination of lambda 3 with the bonding pi orbital? The bonding combination will give you constructive interference with respect to all of the different carbon-hydrogen bonds, and will result in an orbital that basically looks like two bananas. One banana on the top, and one banana on the bottom. My art skills aren't very good. It's bonding with respect to the carbon-carbon bond in a pi fashion, and it's bonding in kind of a sigma fashion with respect to all of the carbon-hydrogen bonds at a single node. So that's a relatively low energy orbital with just a single node. The anti-bonding combination, lambda 3 minus pi y, looks like this. It still has that horizontal node that it had to begin with, and now it's got destructive interference with respect to all the carbon-hydrogen bonds, and the result will look something like this, where some of that pi orbital will have been removed. Not as high energy as this one, because there are fewer nodes. We don't have this vertical node in the anti-bonding combination of lambda 4 with pi star y. Here we don't have it. So that's the combinations that can be made using the pi y and pi star y orbitals. Combining with either lambda 3 or lambda 1. Oops, that's supposed to stay there. So here are two of our molecular orbitals, and here are two more of our molecular orbitals. The result so this was lambda 4 plus pi star y. This was lambda 4 minus pi star y. now we need to do the combinations of lambda 1 plus sigma 1g, lambda 1 minus sigma 1g, which will be equivalent to lambda 1 plus sigma 3g, as it turns out. And then we need to do lambda 1 minus sigma 3g. And on this side, we need to do lambda 2 plus sigma star 2u. We need to do lambda 2 minus sigma star 2u, which will turn out to be equivalent to lambda 2 plus sigma 4u. And then we need to do lambda 2 minus sigma 4u. Degenerate solution there, and there'll be a degenerate solution here that will result in the same overall shape and structure of the orbital. So lambda 1 plus sigma 1g looks like that. It's the usual situation where you get an orbital that allows the electrons to extend over all of the atoms of the molecule. Bonding with respect to all of the bonds, the carbon-carbon bond and all of the carbon-hydrogen bonds. This will be the lowest energy orbital. And it's the orbital that is not described adequately using valence bond theory, because valence bond theory localizes electrons in an individual single bond rather than letting them spread out over an entire molecule and all the nuclei. Even this is lower energy than you would predict using valence bond theory, because now these electrons are able to interact with multiple nuclei at the same time, more than two. So there's lambda 1 plus sigma 1g. Let's look at lambda 1 minus sigma 1g. Lambda 1 minus sigma 1g looks like this. We're out of phase. We're creating new nodes on all the carbon hydrogen. So lambda 1 minus sigma 1g is going to look like this. And then some of that electron density for sigma 1d will have been chopped out a little bit. So we'll have an orbital that's kind of lost some of its electron density. And we have new nodes. Still bonding with respect to the carbon-carbon bond, but anti-bonding with respect to all of them. Let's look at lambda 1 minus sigma 3g. Lambda 1 minus sigma 3g look like this. Has nodes through the nuclei. And we're creating new nodes here. So that's a higher energy situation than this, because of the presence of the two nodes already, in addition to the new ones that we're creating. So what that's going to look like when we're done is this. lambda 1 minus 3 sigma 1g is the same as lambda 1 plus sigma 3g. I could have gotten to that same orbital by adding it to the sigma 3g orbital. Lambda 2u plus sigma 2u would look like that. We get nice constructive interference here. So bonding with respect to all the carbon-hydrogen bonds, but anti-bonding with respect to the carbon-carbon bond, because we still have that same load. That orbital ought to be at least roughly degenerate with this orbital, because they each have a single node. And it will look like this. With the existing nodes still present. So it's very similar in shape to the results of sigma lambda 3 plus pi y, but it's rotated 90 degrees. So we've now created, if I erase the precursor, and just leave the final molecular orbital present. Erase the precursor here. And just leave the final orbital present. We've got our lambda 1 plus sigma 1g. We've got our lambda 1 minus sigma 1g, same as lambda 1 plus sigma 3g. We've got our lambda 1 minus sigma 3g. So those are the three orbitals that came from that interaction. We've got lambda 2 plus sigma star 2u. So we have to have lambda 2 minus sigma star 2u and lambda 2 minus sigma star 4u. And then we've got pi 3 plus and minus pi y. And we've got pi 4 plus and minus pi star y. We've got 9 orbitals up there. Sorry, we got 8 orbitals up there. That one left the results there. So let's do the remaining 2. Right, there are 12 total orbitals in this system. 10 of them are in the plane, 2 of them are out of the plane, those with a pi z, pi star z orbitals are unchanged from C2 dimer. So I now need to do lambda 2 minus sigma 2u. It takes minus 2u. Takes the anti-bonding sigma orbital and interacts it out of phase with the ligand group orbital that has this node in the same location, which is the vertical YZ plane. And the result of that existing vertical node is still present. Created new nodes. We can do for that. You'll notice that often the resulting orbital for the anti-bonding situation looks a lot like the orbitals from which it's created. All we've really done is chop out a little bit of the orbital where they're overlapping and we get destructive interference and showed it as a node, so there's zero probability now of finding the electron there. And then the last orbital we have to do is lambda 2 minus sigma for U star. And interacted destructively with the anti-bonding sigma 4 orbital. It already has 3 nodes. But now we're going to create bad interference here, right? So there'll be destructive interference in that case, and bad interference here. So there'll be lots of destructive interference. Resulting in a lot of places the electron can't be, and the electron gets pissed when you tell it it can't be places. The feature of electrons is they don't like being told they can't go places. A little bit like fools in bars without masks on. So there are the new nodes. There were the 3 nodes that existed to begin with. So this is the result of lambda 2 minus 4u. So a whole bunch of crap on the board right now. I'm going to take away the before picture and leave just the after picture. So we'll just have 10 orbitals up on the board. I'm assuming I took away everything I meant to take away. There's 11 things on there. This is the before picture and I need it. There we go. So those are the 10 in-plane molecular orbitals that we've created. The lowest energy will be this lambda 1 plus sigma 1g. Right? No nodes, electrons delocalized over the entire molecule. Going up a little bit in energy, we have these 2 orbitals that have a single node, lambda 2 plus sigma 2u star, which has just a vertical node, and lambda 3 plus pi star y, which has just a horizontal node. Those will be the next highest energy. But they're still bonding with respect to all the carbon-hydrogen bonds. And this one actually is probably a little bit lower in energy than this one because it's bonding with respect to the carbon-carbon bonds. It's a pi bond with respect to carbon-carbon bond, but it's still bonding with respect to the carbon-carbon bond, whereas this combination is anti-bonding with respect to the carbon-carbon bond. So this will be a little lower in energy than this one. It's a little bit more bonding in more places. So lowest energy. The next lowest energy is this one. So that's MO number 2. The next one is this one. This is MO number 3. The highest energy situation that we could possibly have would be the one with the maximum number of nodes. And you can see that lambda 2 minus sigma 4u has lots of nodes. It had 3 existing nodes and created 4 new nodes. So this is probably the highest energy. Which would make it MO number 12. This situation is bonding with respect, but it has a lot of bonding character. So can we see any other orbitals that have similar amounts of bonding character? And the answer is no. So this should be molecular orbital number 4. The 4th highest energy. We know that the middle, molecular orbital 6 and 7, are pi z, pi star z, respectively. Because the pi system is always in the middle. We've got 5 orbitals that are lower in energy than the bonding pi z, and 5 orbitals that are higher in energy than the anti-bonding pi star z. So we need to identify the 5th one, the one that has significant bonding character in addition to the anti-bonding. Probably this is anti-bonding with respect to all of the, and sigma bonding with respect to the carbon-carbon bond. So that would be the fifth highest energy situation. The only other orbitals that have any bonding character at all are this one, which has some bonding character with respect to the carbon-carbon bond, even though it's anti-bonding with respect to all carbon-hydrogen bonds, and this one, which has some high bonding character with respect to the carbon-carbon bonds. So these two will be kind of the next lowest energy. This one had an existing node in addition to the new nodes that were created. This one had no existing node, right? So this one is definitely lower in energy than this one. But this one's not too bad. So that's probably molecular orbital number 8. So then we're left with lambda 4 plus pi star y, lambda 1 minus sigma 3e, lambda 2 minus sigma 2u star. We've got to rank those in general order. This one's got a little bit of bonding character that the others don't, which will lower its energy a little bit relative to the others. You'll know what the possible locations. This one actually has 8 separate lobes. This one only has 6 separate lobes. Which means there's an additional node here that isn't present in this one. So that's molecular orbital number 10. This one's molecular orbital number 11. There are actually no degenerate pairs of orbitals in ethylene. Every orbital is at a separate energy level because none of them have the same combination of bonding and anti-bonding interactions with respect to all of the different atoms. Always the lowest energy is the one with the minimum number of nodes, and then you go up in energy as the number of nodes increase. But the two single node orbitals in this case are not bonding and anti-bonding in equivalent fashion, so they are not degenerate. And then you'll see as we go up, we gradually increase the total number of nodes. Right? So there are more nodes in MO number 4 than there were in 2 and 3. And MO number 5 has more nodes than the rest. So congratulations if you got all the way here. It's not actually required to understand this, but hopefully you've seen the general system, the method that we use to approach making molecular orbitals from atomic orbitals. And if you play with it for long enough, eventually the light will click on and you'll wonder why you didn't understand it in the first place. But if you get to ethylene, right, you're really doing very well. Most